Hey, what's up? Good morning. This is Brian Aconico from the section A1 at the Unit 81 of Professor Purpose. So today I'm going to discuss about some differential equations, particularly homogeneous Bernoulli equations and some linear differential equations, and some applications also. So let's get. Alright, let us start differentiating differential equation. But particularly, let's start with the homogeneous differential equation. Now, what is a homogeneous differential equation? Homogeneous differential equation is a first-order differential equation of degree 0, and it has the form dy dx is equal to n function of xy over n which is a function of x and y also. Now this equation is equivalent to n xy dx is equal to n xy dy. Now if you notice, this is similar to the equation of the exact differential equation. Yes, that's right. They are the same, but the difference between exact and homogeneous differential equation is that if you solve the exact differential equation and you take the partial derivatives of m and n and you get the not exact or inexact partial derivatives, then your equation will fall into a homogeneous differential equation. Yes. Now, multiplying each variable x and y with a constant lambda will leave the function unchanged, where lambda can be chosen arbitrarily to simplify the form of the equation. Therefore, m lambda x lambda y is equal to lambda to the n, where n represents your exponent of the reals, m x y. Now this will give us the equation dy dx is equal to lambda n and x and y over lambda n x y. Now we just substitute the given values or the above values to the equation or to the original equation. Now this is just equal to dy dx is equal to m x y n x y, as what I have said. Now let's take an example. If m xy dx is equal to n xy dy is a homogeneous equation, prove that if it is expressed in terms of polar coordinates r and theta by means of substituting x is equal to r cosine theta and y is equal to r sine theta, it becomes a parabola. Alright. Now let's solve this problem. Now, you have the general formula for the homogeneous differential equation, which is the m xy dx is equal to n xy dy. Now the problem says that if we take or we make this equation into a polar coordinate by letting x is equal to r cosine theta and y is equal to r sine theta, then if you substitute the given values and taking the derivative of x and y, we can get the dx is equal to negative r sine theta d theta plus cosine theta dr. That is just by the derivative first derivative second derivative first. Same thing you apply to the dy is equal to r cosine theta plus sine theta dr. Now, substituting those equivalents to x and y. Right now, you have the resulting new equation in terms of polar coordinates. You have the m, r cosine theta, r sine theta. This is your x and your y. Minus r sine theta d theta plus cosine theta d theta, which is your dx, is equal to n r cosine theta r sine theta r cosine theta d theta plus sine theta dr, which is your dy. Now, evaluating the above equation, or evaluating the resulting substitution of your r, x and y, you have the negative m r cosine theta r sine theta d theta equal minus, because you transpose the n to this, it becomes negative, and it becomes n r cosine theta r sine theta r cosine theta d theta plus sine theta d theta minus cosine theta dr. Now, factoring out the r, you have the result of negative m r cosine theta r sine theta d theta minus n r cosine theta sine r sine theta cosine theta d theta equals dr. Factoring the dr out, we are sine theta minus cosine theta. Now this will give us the result negative m r cosine theta r sine theta sine theta d theta. If you notice, you transpose your r to the right and you transpose your sine theta cosine theta minus cosine theta to the left, which will give you now a separable differential equation of the form theta d theta is equal to m r cosine theta r sine theta sine theta minus n r cosine theta r sine theta cosine over sine theta minus cosine theta is equal to dr over dr, which is now a separable differential equation. And that's it. That's how you transform a homogeneous differential equation to a separable by means of substituting x and y into a polar coordinate equivalence. Now, next up, we have the Bernoulli differential equation. Now, what is a Bernoulli differential equation? Bernoulli differential equations are like linear differential equations, but with a little change in the general formula, which is having a y sub n, y to the n to the right of the equation, thus giving you a general formula, a general equation of dy dx plus p of x y is equal to q of x y to the n. That is how your Bernoulli equation should look like. And this is also your linear equation dy dx plus pxy plus qx. Now, you notice the difference, y sub n here in the Bernoulli and in the linear differential equation there is no y sub n. Now, how to solve this one? One can solve the Bernoulli differential equation by reducing first the equation into the general formula, which is this one, the above, this mentioned above, then letting y is equal to z 1 minus n. Now you can use any variable here. You can use w, x, you can use y, but this is actually the most common variables used. So letting your y is equal to z 1 minus n, and then getting its derivative, dy is equal to derivative of z 1 minus n. Now you do the calculations. By substitution, you can now obtain an equation which is a linear equation. Now let us take this as an example. Y squared y1 is equal to y squared plus 2xy. Now let's solve this one. This is your Bernoulli equation. X squared plus y1 is equal to y squared plus 2xy. Now rearranging this one into your standard form, x squared y squared is equal to minus 2xy is equal to y squared. Now in order to get rid of the x squared here, you have to multiply the whole equation into 1 over x squared, which will give you the standard form of your linear differential equation, from Bernoulli to your linear differential equation. Now you have the dy dx plus the general formula always has the plus in the middle, times negative 2 over x, y is equal to y squared x squared. Now again, rearranging this one, make it more easier to look. You have the dy dx plus negative 2 over xy is equal to x negative 2 y negative 2. Now you have to look, this is your y to the n, right? Now your n represents the exponent, which is here in this case equals to 2. Now we will let, in order to solve this one, we will let y is equal to let y equal to z 1 minus 2. You have to let y is equal to z 1 minus 2. Then you have y is equal to z negative 1 to the negative 1. Now getting the derivative with respect to x, dy dx is equal to negative z minus 2 dz dx. Now by using these conventions and substituting it to the equation, you will have now your new Bernoulli equation, or your new linear differential equation. Now by substituting those given values, you will have now your new equation, which is the negative z minus 2 dz dx plus negative 2 over x z negative 1 is equal to z to the negative 2 times z to the negative 1 squared. Now this is your y, this is your dy dx, also this is your y again, from the given from the equivalence that you have get. Now in order to eliminate again this negative z to the negative 2, you have to multiply the whole equation with 1 over negative z to the negative 2, which we have then obtained, which will result to the z dx plus negative 2 z, negative 2 over x z is equal to negative x to the negative 2. Now this is a linear differential equation. Now, same process in solving linear differential equation. You have the first finding the integrating factor. V is equal to e to the negative, because this is negative, so that's why you have negative integral of 2 of x dx, which will give you the e to the negative 2 ln of x. Now, which will give you the final resulting integrating factor z minus 2, z to the negative 2. Now, multiplying the integrating factors of the whole of the equation again, you'll get the derivative of your integrating factor times your dependent variable, which is z. This will always be considered your independent variable. dy is equal to y, right? So here in this case, you have, since we let y is equal to z, you have z is equal to the integral of the right side, negative x to the negative 4 dx. Now, the resulting would be z over x squared is equal to negative square root of transpose time. When you separated the negative sign, you have x to the negative 4 dx. Now, the resulting will be z over x squared is equal to z minus 3 over 3 plus c. Don't forget to write c. Now you have the z cross multiplying, z is equal to x squared over 3x cubed plus c x squared, which will give you the result z is equal to 1 over, you can cancel out this x squared and the x3. You have 1 over 3x plus c x squared. Now, don't forget to come back, or don't forget to go back to your original value, which is your y. So, substituting back the equivalence of your z, you have the here 1 over y is equal to z is equal to 1 over y is equal to 1 over 3x plus cx squared. Now, this evaluating this one will give you your final general formula or general equation. Y is equal to 3x over 1 plus 3x cubed c. Now, that's your solution. Now let's move on to the next problem. Now let us find the general solution of linear equation. This one, y squared plus y prime plus y squared over x minus 1 is equal to x minus 1. Now, as you notice, the equation is in the second order linear differential equation, or in the second power. Alright, now we'll try to solve this linear differential equation. X double prime plus 1 over x minus 1, y prime is equal to x minus 1. Now, you may be wondering how to solve this one, because it is in the second order differential equation, or it's in the second power. It's just a matter of letting or changing their variables by letting u prime is equal to your y double prime and your u is equal to your y prime. Now, substituting this to the equation, you have your new equation here, the y prime plus 1 over x minus 1 u is equal to x minus 1. Now, this is just a linear differential equation, and following instructions on how to solve linear differential equations. Finding first the integrating factor, you have here e to the integral of dx over x minus 1 is equal to e to the ln of x minus 1. Now, you have the final integrating factor x minus 1. Now, multiplying this integrating factor to the equation, u1 plus 1 over x minus 1, u is equal to x minus 1, x times x minus 1, and you have the resulting derivative of your integrating factor times your independent variable is equal to your integral of your x minus 1 squared. Look at this. Yes. You have your resulting x minus 1 u is equal to x minus 1 cube over 3 plus c. And don't always forget the c. You have now your equation x minus 1 u is equal to x minus 1 cube over 3 plus c. You now have your general formula u is equal to x minus 1 squared over 3 plus c, x minus 1 to the negative 1. That is just your general solution. If you want to find a particular solution, then you have to find c, but in our part you're just asking about, we are just asked to find a general formula. Now I have here a question. Does the equation y prime is equal to 1 if x is lesser than or equal to 0 and y if x is greater than or equal to 0 have a solution which is continuous on negative x and x, positive x? Now, does it have a solution with the continuous derivatives of negative x and negative z? I mean negative x and x. Now let's try to solve this one. You have here the y prime is equal to on your 1 if x is lesser than or equal to 0 and y if x is greater than or equal to 0. Now, when x is lesser than or equal to 0, you have here the negative x, the negative values of x, and your y. dy dx is equal to 1. Then integrate. This is just a separable, separating variables. You have dy is equal to dx. Evaluated from 0 to y because of this. This is from 0 to y. And your dx is from negative x to 0. Now you have your y is equal to here y is equal to 0 minus x. Therefore the x is equal to your negative y. This implies that y prime is equal to 1 is continuous on negative x or 0 greater than x lesser than n. This implies that y prime is greater than 1 is continuous on negative x or 0 x negative. 0 is greater than or equal to x and x is greater than or equal to n, where your n is your natural numbers. Now when x is equal to 0, you have your when x is greater than or equal to 0 or greater than 0, it means that your x is all positive. Then you have dy dx is equal to y. Now getting the separating the variables, you have the integral of dx, the integral of dy over y is equal to integral of dx. Now ln of y is equal to x plus c. Now this resulting equations, this result will give us a conclusion that ln of y is continuous at x if y is greater than 1, y is greater than or equal to 1, but discontinuous if y is greater than or equal to, discontinuous if y is lesser than or equal to 1 or 0 is lesser than y but lesser than or equal to 1, but y is lesser than or equal to 1. So therefore we conclude that y prime is equal to negative 1 when x is greater than or equal to 0 and y is when x is greater than or equal to 0. Therefore, we conclude that y prime is equal to 1 when x is lesser than 0 or equal to, and y when x is greater than or equal to 0 has no solution with the continuous derivatives on negative x and x. So that's all. That's the end of my tutorial. I hope you have learned something from me, and thank you very much. See you next time.